AC voltage applied to capacitor. When we apply the AC voltage capacitor, how it behaves, we need to understand here. So you need to understand in the sense first we should know that what is a capacitor, how it functions. Capacitor is a device which shares us or which which stores the electrical energy. Yeah, the charge is in a form of electrical energy, right? So here, if we apply AC voltage to whom applied to capacitor, capacitor, how it will be, that we need to discuss. We know the capacitor is a device which stores the charge, nothing but which stores the electrostatic energy in the form of charge. So for this, I am applying the AC input, means AC voltage. Let's say the charge is, this is positive place, this is negative place, it gets charged, between them potential difference develops. Then charge develops on the two places, positive and negative place. Between them, automatically there is charge, electric field develops. So in such a way, the current will move here. Once capacitor filled, it's like a bucket of water we discussed earlier. Once this bucket is filled, what happens? There is no flow of current, right? So now what I'm trying to say here, when we have, since this is a voltage we are supplying from the source, flows current in that, and this is a charge which develops here, positive charge, here negative charge, that we know. Now usually the instantaneous voltage across the capacitor Q equal to CV, the charge, right? If you write in terms of voltage, then V as a subject. So when you write V as a subject, V equal to Q by C we will write. Now we know that from Kirchhoff's laws, when you apply across this total closed circuit, the total voltage that we can write in terms of voltage, since we are supplying from the AC in the sense maximum voltage Vm sine omega t, we will write V stands for, and that is equal to the charge develops on the capacitor is Q by C we are writing. We know that we need to express this is in terms of current, in the sense we have to differentiate. For that purpose we know I equal to dq by dt. So how can you get I equal to dq by dt? That means you have to apply differentiation both sides. Let us say differentiating both sides in the sense I am differentiating dq with respect to the time, then I am sending the c this side. So d by dt of c into Vm sine omega t I can write. Means already I sent c that side. Then after that I differentiated. Why I have differentiated? To express this equation is in a form of current. So dq by dt is nothing but current. That is I equal to, what we can say, since it is dq by dt. So d by dt of Vm c sine omega t, this we know. So when you are differentiating sine omega t, what it become? Vm obviously it is maximum as it is if you keep, and c is the capacitance of the capacitor. Sine omega t, if it is differentiated, omega will be a constant like this. Sine omega t differentiation is that cos omega t. This is our current wave equation. Vm c omega cos omega t. With respect to the current we can describe. Now we know I equal to Vm c omega cos omega t. I can write this expression in another way in the sense, just in terms of sine component, like you can see here, I equal to Vm c omega cos omega t. Cos omega t I can write sine omega t plus pi by 2 means sine 90 plus theta I can write up. So therefore, if I write sine 90 plus theta, that is gives us cos theta is here form. So whereas voltage equation which I am having, Vm equal to sine omega t by q by c, and current equation I equal to Vm sine omega, Vm c omega into sine omega t. Means from this sine to this sine, there is a 90 degrees difference. Means here 90 degrees the current or pi by 2 radians the current is ahead the voltage. That if we represent in a form of voltage equations in the sense, let us see I equal to what we are having Vm c omega sine omega t plus pi by 2 is the current equation. This I can write in terms of Vm by 1 by omega c, this part equal to I can write xc. What is that means? B equal to IR we know, right? Therefore I equal to V by R. Same way here I equal to Vm by 1 by omega c. 1 by omega c is nothing but capacitive reactance, that we can say that resistance in the capacitance simply. Vm by xc we call it simply. Okay. Now this gives the resistance in the capacitor circuit that I am writing here. So I equal to, instead of writing, I can say I equal to this part, since Vm by y omega c in the sense this I am making as a Im. So this part is we can write as Im into sine omega t plus pi by 2. That is this part I have changed to have maximum current. Okay, by using this fact from the Ohm's law. This is from the Ohm's law we can write up. 1 by omega c is stands for xc equal to 1 by omega c. This is a resistance in the capacitor circuit. XL equal to omega into L. This is a resistance in the inductor circuit. Now we know already V equal to Vm sin omega t equal to Q by C, right? That is a voltage based equation. Now comparing with these two equations, when you obtain the vector diagrams, I mean phasor diagrams, phasor diagrams, let us say this is in terms of omega t direction. If you see, this is a one vector in the sense means voltage vector. Let us say Vm sin omega t. Perpendicular to this means at 90 degrees level, like this. From here to here it is pi by 2. It gives the Im sin omega t plus pi by 2. This gives. Means here current vector is lagging, sorry, ahead the voltage vector. Here voltage vector lagging behind the current with the pi by 2 radians. Whereas in inductor, what happened? Current is lagging behind the voltage. Current is lagging behind the voltage, but in the capacitor, current is ahead than the voltage with the pi by 2 radians. Okay. If you obtain phasor diagram, this is a phasor diagram, and this gives current vector and with respect to graph Obviously voltage amplitude is more. This gives a Vm. Okay, this is we can say that phasor diagram with respect to the equations in the capacitance of the capacitor. Now, what we understood here, when we are supplying any AC to the capacitor circuit, then always the current vector is ahead than the pi by 2 radians ahead than the voltage vector. If you obtain graphically, means if you draw a graph, this way we will write. Means we'll get down more and like this. And current in the sense little difference. How much difference you will get? Current vector starts here. Voltage starts at zero in the sense current starts at here like this. So this is we say is a current and voltage vectors. Same way, power coming to the power. Here also in this case also same power average power equal to average power P equal to V I we will write. And voltage vector and current vector if you write, then that can be further V equal to Vm sin omega t we will write into I equal to Im sin omega t plus pi by 2. So this is all as a part of average power. Then again if you apply formula sin omega t into sin omega t, then it will be changes. It gives the different value. Means Im sin omega t plus pi by 2, I can write cos omega t. Then Im Vm into sin omega t into cos omega t. Then from this we have to write the formula. So this is also gives averagely equal to 0 from the average power in the capacitor as well as inductor. It is equal to 0 because over a complete cycle it is 0 because we have studied sine 2 omega t or cos 2 omega t. This gives us for the complete closed cycle it is 0. So therefore average power is 0 in the case of capacitor circuit also. Now let us discuss a small example here. It is given the question. What is the question has given? The question is that a lamp is connected in series with a capacitor. A lamp is connected in a series with a capacitor. Okay. Next, predict your observations for DC. Your observations for DC, for direct current, and AC connections. How it is? What happens in each case? What happens in each case? Each case, if the capacitance of the capacitor is reduced, if capacitance of the capacitor reduced, you can see here just a lamp is connected in series with a capacitor and to DC connection. DC connection is direct current. In the direct current, when you have connected with the capacitor, Of course, capacitor blocks the DC. Here, there is no effect of the capacitor in the case of lamp, right? But if it is connected with the AC, when you connect with the AC, what happens until it plays, it supplies the AC to this, it's fine. But in AC case, how you will find that bulb? In DC case, since it is blocks, there is no difference in the intensity of the bulb. But in a AC case, when the capacitor stores, that time we can find that the bulb is glowing. Once it is stored in the capacitor, the charge, after that it stops its charging, right? So if it is stops it charging, in the sense there is no flow in the no current flow in the circuit. Since no current flow in the circuit, what happens? Will the bulb will glow?
No, sir.
No, it will not glow. But in a DC case, it will not respond. Means capacitor, it will not use of. There is no use of capacitor. But in a AC, it is there is a use. It is response for the. It gives a response for the alternating current, but direct current it will not. And in the same case, it is also given what happens in each case if the capacitance of the capacitor is reduced. What will happen if it is capacitance of the capacitor is reduced? With respect to DC, there will be no change because with the DC there is no response with capacitor. And if with respect to AC, what happens? With respect to AC, there is a resistance will act. Which resistance? Capacitive reactance will act 1 by omega C, which we have discussed, right? But until the capacitance of the capacitor is reduced, it shines brightly. But what happen if it is continuously decreases? What happen? The capacitor initially shines much, later on it is decreases its intensity. Which intensity? The brightness will decrease in the capacitor, right? Next.